Okay. Yeah. Okay. Sorry. Right. So hi everyone. I'm Camille Landri. I'm a postdoc at KU Leuven. And I'm generally interested in stellar interaction and binary stars. But since I started working in Leuven, I got a little bit of an interest in chemistry. Very little, because I actually don't really like chemistry, but it's pretty useful for what we do. So I started working on it and picking up Silke's work with MACE that she just described, and start to couple it with phantom so that we can run chemical reactions in 3D, basically. So I'm going to give a brief introduction because I think Silke did a great job, and Owen yesterday as well. So I will summarize their introductions with that sentence. We have cool evolved stars like AGB stars and red supergiants as well. Dust and plenty of other things happen. And one of the important things that I've been told happens, actually, and I didn't know before, is that chemistry impacts the dynamics in a lot of different ways. So if we look at just this is not to scale, but an outflow, we have, of course, the molecular reactions who impact the thermodynamics of the wind, for example. Then the different molecular abundances also impact the dust formation, and then different dust formation will lead to different wind properties since it relies on dust-driven processes. We also have molecular cooling and heating due to like vibrational and rotational transitions. And of course, we have photochemistry on the outer edges from the interaction with ISM radiation, for example. And we also have companion interactions, which drive these spirals that have like very dense parts and very large underdensities in some other places as well. And so this has feedback on the chemistry, because then in places we have very different conditions than others. So there's really a feedback between the chemistry and the hydro in both ways. And so it's important to solve the chemistry along with the hydrodynamics of the outflow. We can do that by considering classical astrochemistry. Silke talked about it a little bit, but by classical, we mean solving the actual chemical kinetics under some specified physical conditions. So basically how the abundances evolved when the outflow around evolves as well. So we can consider only like 1 and 2 body reactions, for example. So photon-induced reactions for the one body, and then just your regular molecular interaction that can be parameterized as a function of temperature. And then we get that sort of half ugly, half nice equation that you can summarize with sums. And so you get the number densities represented as m's and the reaction rates with the k's. And so the number of species determines the number of equations in that system, and the number of reactions that we're considering determines the amount of elements in each sum. So you can guess that this scales quite quickly with the precision of the chemical networks that we are using. And the classical chemical kinetics have one main issue, is that the ODEs that I just showed you are very stiff. And that's due to one main thing, that's some reactions require very small time steps, and some reactions require very long time steps. But then we need to resolve everything on the shortest time step possible, otherwise our solutions may grow unstable. This means that our time step can basically be super small and will be super small. And on top of that, we have a parameter space that can range over very large scales. If we consider stellar outflows, for example, we have quite dense and hot wind on the inside, and on the outer part of the outflow, we have these lower density parts that are very cool. So we also need to take into account a lot of different density, temperature conditions. So overall, it's a computationally expensive model to run chemical kinetics. And so far, it's been mostly done in 1D for AGB stars, as Silke showed. She removed her efforts from the thing and showed only Marie van de Sande's papers, but she did it as well. But as she talked about before, and Owen has talked about, AGB outflows are not spherically symmetric at all. we have all of these amazing observations of these wild shapes around AGB stars. So it's pretty clear that 1D for the chemistry there doesn't work. So we need chemistry in 3D. We can already do astrochemistry in 3D. Some of you probably know that phantom has been coupled with chrome, for example. Whether it works out of the box is another issue, but the coupling exists. But these simulations are incredibly expensive. There's the first thing I talk about, which is like just the computational cost itself, the stiff. So they require quite a considerable amount of calculation for just one-time step over one fluid element, but then we need to do that across the whole domain. So that scales up pretty quickly. The other, and actually, so my colleague Matt Sesselders did some post-processing of our phantom models with Chrome, and he came up with these numbers. So one particle for one time step on one core and about 600 species. So that's quite a lot, but it is also what we need. It takes about 0.1 second. So you can imagine how that scales for 2 million particles over like thousands of dumps. That's like mad. And that's just post-processing. That's not even coupled. And the second problem is the memory usage, because we need to store the abundances of like hundreds of chemical species for each fluid element. So imagine the size of your dumps when you put like 600 species in there for each particle. That's also stupidly high. We can maybe possibly sort of reduce these limitations. We can reduce the size of the network, we would suggest probably. And I will say no, because we need to account for all species that may not necessarily be considered as important because they're not necessarily a tracer of the physics within the outflow, but they can be catalysts, for example. And if we remove those, then somehow our network will give the wrong predictions. And we may also just undermine the contributions of very important physical tracers there. So it's not for now an option. We could increase the time step of like Chrome, for example, but then, as I said before, unstable solution, so not really an option either. And we could only do post-processing with the chemical kinetics, which is what my colleague has done. But it's still quite expensive to do, and we lose the feedback between hydro and chemistry. So it's not interesting in our use case, at least. So we do need to step away from classical solvers, at least for some use cases. And that's why Silke built her chemistry emulator MACE, which is what I aim to couple with Phantom. So I will repeat a bit of the things that she said because we have overlap. It's a bit sad, but chemistry emulators in general are surrogate models. They're neural network that emulate the evolution of a specific chemical network. So it's been trained to emulate something super specific, and the architecture itself can vary from the use case. But Silke's is actually quite advanced. A lot of them are a lot more simple and basic. But then you train that model, and to train that, you need the output of classical kinetic models. So we're not replacing the classical method. We're just using your focus on really the type of problem that the emulator will focus on. That's very important. Be used on like your 3D or 1D simulations, depending on what's in the it's been trained on, and just takes repeat a couple of things that Silke said, just so that we're all on the same level. So it's been trained to reproduce a chemical network of 468 species with more than 6,000 reactions. So it's quite a dense network. And so it uses these abundances as input with 4 physical parameters, and then the encoder with an 8-parameter problem. Then we have an ODE solver that evolves these 8 parameters over a delta t. The good thing about this ODE solver is that the coefficients can be trained if we want to further optimize the problem. And then we can decode the result of this ODE solver back to the 468 abundances that we wanted before. MACE for now has been trained only on data from 1D AGB outflow. I'm showing a different result from Silke, but so you have variety of how good it is. But it's very good at reproducing the output of our chemical kinetics. So if it's wrong, it's not because of the network, it's because the chemical kinetics are wrong. Just note that this is not our fault. But overall, the emulator is about 25 times faster than the classical solver it's trained on. So that's already a big improvement. And its architecture is made to be flexible, so we can use it on other environments as well. We just need to tweak a little bit the hyperparameters of the model. And most importantly, there's an ODE solver. So that means that we can actually run MACE on variable time step, which is important if we want to solve the dynamics of the problem. So it can be coupled with 3D hydros fairly simply, thanks to that main feature. Now, what do we actually want to do with Phantom and MACE together? So we need to retrain MACE on 3D outflows first, of course. But then my goal is to implement the emulator in Phantom. So you saw that the emulator had different parts, so it will be split up. That's a bit more complicated than just put MACE right in the middle of Phantom. But basically, we want to call the network at every time step, start from a hydrodynamical state, then let MACE predict the new abundances in latent space. Then we store the latent abundances so that we don't have the cost of the 400 species and whatnot. And we decode them for the thermodynamics when we need cooling rates and when we need dust condensation, for example. That's one of the many things. I'm sure you can all find plenty of other places where it would be useful. And so using MACE instead of Chrome, for example, has two main benefits. It's naturally faster and can parallelize better. So we solve 8 equations instead of 468. Already the benefits seem pretty clear. And it has, of course, a much more efficient memory usage. And Maya, remember that this is for each particle. So really multiply that by 2 million. It also, of course, comes with massive terms of use because this is machine learning and neural networks needs to be handled with care. I'm not saying that nobody else should be using it. I'm saying that we need to be aware of the limitations of the model and how it should be used. So the first thing is that whenever we use it for something new, we need to retrain it and probably also adjust the hyperparameter of the model. So that's the number of layers, number of nodes, the activation functions and whatnot. So the network will need to be optimized for each problem. It's not necessarily an issue. It can be done fairly fast. I think it's just a bit of trial and error, but it needs to be retrained every time you switch from 1D to 3D, add a chemical reaction, a new species, and whatnot. And the training, super important, must include the physical condition that MACE will have to reproduce. So for example, don't use MACE that has been trained on AGB outflows on ISM simulations. You won't be able to trust anything that it spits out. And another important example is that if the gas undergoes shocks, then MACE needs to be trained to treat discontinuities, basically. So in our case, where we have the companion with the gas, this is a very important part. And so that's the main overhead of using MACE. We need to generate a lot of training data. And this training data needs to be thought carefully and planned ahead and blah, blah, blah. So I think that's the main caveat of the whole thing. And I'm concluding on a sort of sour note, but really I think if we can make it work and have pipelines so that we can treat different sort of astrophysical environment, this would be a great way to solve chemistry faster because really it's a massive bottleneck. And I'm leaving you with the roadmap, which is getting longer every time. And then because everyone makes little logos of Phantom, I made my own. And now Phantom is a chemist. So thanks for listening.
Exactly on time as well. We got some questions. Next.
Thanks for the talk. I'd like to ask if there's been any detailed study into understanding which of these 468 chemical species and the vast number of reactions are actually very dynamically important for the simulations, because the whole point of doing the chemistry live is to be able to capture the feedback of the chemistry onto the hydro.
Yes.
So do we need all these reactions, or can we do most of them in post-processing?
So Silke can correct me if I'm wrong, but Marie van de Sande did some sensitivity studies to check which of these chemical species are important, but she did them in 1D. So there's no companion interaction and whatnot, so they need to be redone in 3D. I'm sure that once we find out which chemical elements are more important than others, we can reduce the network. But until then, no.
Okay, thanks.
What was the conclusion in London?
I don't remember. But she uses like these sort of networks that are massive, and so.
Just one last question before going to coffee. Sorry.
Maybe Silke said this, but MACE is using PyTorch, is that?
Yeah.
I'm a bit unfamiliar with PyTorch, but does that introduce any sort of like architecture, like hardware constraints? Like, does it have to be on a GPU? Can you do it on a CPU? Does it matter?
It can be done on CPU. Yeah.
Does it matter the architecture at all for training or using? No.
We can use CUDA if we want to train it, but we don't have to.
Okay.
Do you have any pressing questions? If not, let's thank all the speakers for attending the session again.